What's going on, guys? Welcome to another video brought to you by The Simple Engineer. Today we are going to be touching on the idea of encoding and decoding instructions in MIPS assembly language programming. Now, what that means is when you write instructions like the following, this is using symbolic language. These functions have been programmed into the language to automatically convert them to a machine-readable language. And when you do operations such as checking your email or your Facebook or all these kinds of things, they're actually at the lowest level computing that operation in ones and zeros, bits of ones and zeros. And that's exactly what these instructions are doing in assembly. They're taking these values and they're converting them to 1 and 0 equivalents to compute the operation. And that is the process of encoding. They're encoding these instructions to machine readable language. Now, decoding is the process of taking those binary instructions or hexadecimal instruction equivalents and converting them to MIPS assembly readable instructions. And we'll go ahead and take a look at both of those. So first things first, I have an example that I would like to look at, and this is the idea of encoding. And what we're going to do is convert this instruction into a binary readable format for the computer to read. And then from there, we'll actually convert that binary format into a hexadecimal 8-digit integer. So let's go ahead and get started with that. Now, there's actually some resources that are necessary to be able to do this. And the first being the MIPS reference data sheet. It's a common universal sheet added in many books, and the link for this will be in the description. This shows the opcodes for certain instructions. It shows the instruction formats for the relevant instructions that we're going to be looking at, and it shows just a ton of data that's very useful for MIPS assembly programming. Now, with the idea of instructions and instruction formats, we need to discuss what the different instruction formats are. There are essentially three main instruction formats. We have R, which is register instructions. We have I, which takes care of all the immediate instructions, and J, which takes care of the jump instructions. We're going to mainly be looking at the R and I instruction formats today, but you will get the idea of how J instruction formats work in the process. So the instruction formats, when you convert them, follow this basic syntax. We have an opcode, we have a source register, we have a register that follows the source register, and we have a destination register, we have a shift amount, which is the byte shift from the initial address, and we have a function code. Now, a couple things to note, some rules of thumb here, is for our instruction formats, the opcode is always 0. For I, it's actually whatever the function number is. Okay, so you always want to know that the opcode for our instructions are 0. Now, let's get started here. If you look here in our example, we have XOR is our operation. So we need to figure out what type of instruction it is, if it's an R, I, or J instruction. And once we figure that out, then we start following this syntax to build our encoding. So if we go ahead and open up our MIPS instruction coding sheet, and this will actually be in the description as well, we will go ahead and look through and see if we can find XOR and what instruction format it's associated with. So this first page is associated with R instructions, and I'll go through, and it's alphabetized. And you see here at the bottom we have XOR. Well, there we go. And if we look here, the function code it's already converted us to binary for us, and we have this 100110. And that's going to be our function code. And just like I said before, if you look at the opcode for all the R instructions, you can see that they're all 0, okay? Because that's what the opcode always is for R instructions. Okay, so 100, 110 is our function. So I'll just go ahead and write that 100110. And I'm just going to keep this in the top so I don't forget it. And that's associated with the function code for XOR. Now we need to look at these remaining values. We need to figure out, okay, we know the opcode already. We know the opcode is 0. We know the function code is this value. Now we need to find the binary equivalents for the S7 register, the A3 register, and the T5 register. And to do that, it's very easy. What we do is we open up our reference data sheet and we go here in the bottom right-hand corner of the first page, and it shows these register names and associated numbers. And like I said, the first one is S7. So if we go to our data sheet and we go into S7, it shows the number here. Well, S7 is associated with 23. So if I go here and I write 23, this is going to be the numerical equivalent representation of the S7 register. However, we're converting this information into machine-readable language. This needs to be in binary. So what we would do is we would open up a binary calculator, and the link for this will be in the description as well. And I will just say I will convert decimal to binary converter. And the decimal value is 23, like we said, and I will convert that, and it gives us this binary value. So I'm going to just remember this, and I want to put 0001. So this is going to be 0001, and it ends with 0111. 0111. And if you were to do this on your calculator, there should be a built-in function where you can just convert decimal. You type in your decimal value and you would convert it to base 2. Base 2 is the associated base for binary digit representation. Now we need to go to the A3 register. Well, A3, looking at our reference sheet, is associated with 7. Okay, 7 is the numerical equivalent. And if we type in 7 here, we get 111 as our binary representation. So I'll go back into here, and I would put 111, and this would just be some zeros. Now you may be asking, okay, how many zeros do I put in front of these values? Because these need to be represented in bits, and there's only a certain number of bytes allocated to represent these codes. And to be specific, there's actually 32 bytes allocated. And we know that because if we look at this R instruction format, you see it starts at 31 and it goes all the way to 0. So 0 to 31 including equals 32 bytes. And there are segments of these numbers here. So the opcode is 26 to 31, which means there are 6 bytes allocated for the opcode. So there would be 6 zeros there. And the source register allocates 5 bytes. So if we go here and we look at the source register, which would actually be this value, we would have 1, 2, 3, 4, 5. So we would actually not need this extra 0. We would just have 0, 0, 1, 1, 1. And this is going to be our source register. Now the next register, like I said, the RT always follows the source register. That is going to be T5, and that also has 5 bytes allocated for that specific space. So if we go ahead and look at our green card here, we know that T5 is associated with the number 13, and 13 in binary is the same as 1101, and we want to keep in mind that we need 5 bytes. So 1101, that's only 4, so I'm just going to put a 0 in front there, and this is going to be our RT. So I'm just going to start labeling these. So this would be our RT. This would be our RS, and this would be our RD, our destination register. Because anytime that you perform these instructions, you know that the instructions that you're going to be storing go into some register, i.e. this S7 register, and that's the destination register, the RD, and that is going to be represented right here, RD. Okay, so as you can see here, we're actually already finished. We've done all the hard work. So we need to start putting things in order. So we need to know that when we encode our instructions, they follow the format that we have the opcode first, then we put the RS, then we put the RT, then we put the RD, and if the shift amount is present, we put the shift amount, and then we put the function code last, in this order. So let's go ahead and fill these out. So we already know that the opcode is 00000. Okay, so 1, 2, 3, 4, 5, 6. Okay, that's the opcode for the R instruction. Now for the source register, the RS, you see here, we have 00111. So I'm going to put 00111. Then RT is 01101, and the destination register is 10111. 10111, and the shift amount is not present. There wasn't a shift amount specified in the original instruction, so we need to put zeros there. But if we look at our instruction format, the shift amount has allocated another 5 bytes of memory, or of space. So we need to have essentially 5 zeros here. So we'll say 1, 2, 3, 4, 5. And last but not least, we have our function code. And our function code always has 6 bytes. And as you see here, the function code that we found earlier is 6 bits. So we would put 100110. And what we've done here is we've created the machine readable instruction encode for the XOR statement with these registers. This is how your computer is computing this function. Okay, so now you may be asking, okay, so we've got the binary readable format, but what if we wanted this in hexadecimal? And the easiest way to do this, and just to save time, I'm actually not going to do it, but we would take this value and we would convert it to base 16. And this is not the video to explain base 16 conversion, but like I said, there is a website that easily takes binary to hex, and you'll put that binary number in here and it would output it into its hexadecimal equivalent. Okay, so we've covered the idea of encoding. But now what if we wanted to do decoding, okay? And we'll actually use this same example to better illustrate how this works. So we want to decode the following. And what we'll do is we'll take, I'm going to create a new layer here. And I will say that we are going to be decoding, decoding. And what we're going to be decoding is this binary representation. And what we want to realize is the instruction formats always follow this idea. So if we look at some binary representation, say this is put on a piece of paper, and we want to know, okay, what's the MIPS assembly equivalent to this binary digit? What we would do is we would take a look at the first 6 numbers, because you know the opcode is the first 6 numbers always. And we would see, oh, the first 6 numbers are all zeros. Well, we know that all zeros means that it is an R instruction. However, if the first 6 numbers were not all 0, what if this happened to be 0000, but there was a 1 at the end? Then we would say, okay, well, it's not going to be an R instruction because we know that the opcode for all R instructions are just straight zeros. So this would have to be an immediate instruction. And we would need to find what the associated instruction for that would be. And if we go to our MIPS instruction encoding paper, we'll go over and look at immediate, and we'll go ahead and start scanning these opcodes. And if you look, I just made this one up, so I don't even know if there's one associated with it. Actually, there is. If we look at the opcode here, it's all zeros with a 1 at the end, and that's associated with the numeric instruction of BGEZ. Okay, and that would be the first part of decoding our instruction. But because we used all zeros, all we know at this point is that the opcode is 0, so it's an R instruction. That's all we figured out so far. However, if we want to figure out what type of instruction it is, and in this example, if we were to decode it, it would be this XOR, we need to figure out the function code. Well, if we look at our instruction format, we know the function code is always the last 6 digits of the binary number. And if these were all laid out together, we'd look at the last 6 digits here, and we would have to figure out, okay, what function is associated with 100110? And I would go ahead and open my sheet, and I would start looking at all these function codes. And if we go ahead and browse through them, we'll end up coming to this, 100110. And we would go all the way left and say, okay, this is the XOR statement. So we've now decoded the instruction type, which is R, and we've just said, okay, this is XOR. So the first part is already done. We know that we have an XOR that we're dealing with. So we would put XOR. But now we want to know, okay, what is the source register? What's the RT register? What's the destination register? Okay, well, what we would do is we would say, okay, we know RS is always the next 5 bytes here. Okay, RS is always the next 5 bytes. So we would look at this binary and say, okay, the next 5 bytes are these numbers here. And we have 00111. And what we would do is we would convert that to decimal. And we know that 00111 in decimal, we can use our calculator here. We would say decimal, binary to decimal. We would say 00111, and this should be 7, which it is. We have 7. And we want to know, okay, what register is associated with the numerical value of 7? And if we look at our MIPS green sheet, we see that, okay, number 7 here, here's 7, that's associated with A3. Okay, so we've just decoded the source register. So I can go back here and I can say, okay, fantastic. We know that the source register is 7, which is the equivalent to, and we said it is A3. A3. Okay, so now we're halfway done. We have our opcode, which is 0. We have our source register, and we have our function. Okay, now we need to figure out this RT register. And we know the RT register is the next 5 numbers. Okay, so if we look at the next 5 numbers, we have 01101. So 01101 from binary to decimal is the decimal equivalent of 13. And if we look at our instruction sheet, we see 13 is a temporary register of T5. Okay, well, great. Now we have T5. We have our RT space here for our instruction format. So T5, we would go here and we would say RT is 5, which is associated with T5. And this is actually 13. Okay, so we have T5. And now the last piece is we need to figure out what the destination register is. And to figure that out, we would go, okay, destination register is going to be the next 5 numbers. And I would go here and say, okay, what are the next 5 numbers? They're 10111. And I would go here and convert that. I would say 10111, and that is the decimal equivalent to 23. So I would look at my green sheet and I would say, okay, 23 is the S7 register. Okay, so RD is associated with S7. So now we're done. We don't have a shift amount. The shift amount here, if we look at it, if this was just given to us, it's given as zeros, so we can ignore it. We don't need to put any shift amount in our MIPS instruction. So I would go ahead and start writing out my instruction. So we know it's an XOR, and we know that the destination register is S7. We know that the source register is A3, and we know that the RT register is T5. And if we go ahead and look at our original instruction, it matches up exactly, XOR S7, A3, T5. And what we've done is we've decoded the binary machine-readable instruction into a MIPS assembly instruction for someone to actually read and understand what it's doing. And this covers the idea of encoding and decoding. And hopefully this was clear and easy to understand. And like I said, I will put the reference websites in the description of the video. If you guys have any questions, feel free to leave a comment and I will be happy to help.